So let's look at this example. Industrial waste and sewage dumped into our rivers and streams absorb oxygen and thereby reduce the amount of dissolved oxygen available for fish and other forms of aquatic life. A pollution control inspector suspects that a river community was releasing amounts of semi-treated sewage into a river water. To check his theory, he drew 5 randomly selected specimens of river water at a location above the town and another 5 below. Assume that the population of oxygen level above the town and the one for below the town is normally distributed. The dissolved oxygen readings in parts per million are as follows. And in this case, we want to estimate at the 90% level the difference in mean oxygen content above the town versus below the town. All right, so with every problem, you have to figure out what kind of analysis you're going to do. So you're either doing a hypothesis test or a confidence interval. So the first question you want to ask is, which one are you going to do? So I look for very specific words. In this case, I see the word estimate. Estimating means that we're not trying to make a decision, we're trying to find a value. So that tells me we're doing a confidence interval. So we know we're doing a confidence interval. Now I need to know if it's doing means or proportions. And again, I look for specific words and I see the word mean. So that tells me we have a confidence interval of means. Now we have to decide if we had one sample or two. So the problem talks about selecting specimens above the water and then another random sample below the water. I'm sorry, below the town, not water. So looking at that, that means we had 2 samples. We had a sample from above the town and we had a sample from below the town. So we know we have a 2 sample. So we now know we're doing a 2 sample confidence interval of the means. In reality, it's going to be the difference in means. So now the next question is it an independent or paired confidence interval? So looking at this, we notice we had 5 randomly selected specimens above the town and 5 below. They look like they were very separate. Some people think that this is dependent because it's the same water, but the water actually is different. If they are dumping sewage into the water, then the water below the town would be different than the water above the town because something has changed. The other thing to think about is, does this 4.8 right here, does this number here actually influence at all any of these numbers down here? And that one in specific would not influence any of these numbers. So we could actually say that it's actually an independent test. So we now know we're doing a 2 sample, independent confidence interval of the difference in means. All right. So now we get to actually do the process. Once you figure out the analysis, then the process is always the same. Confidence intervals, the very first step is to state your random variables and parameters in words. So we did notice that what we were measuring was the oxygen levels or oxygen content. So we had oxygen content above the town. And then we did the same thing for the oxygen content below the town. You're going to call one x1 and one x2. It does not matter which one you call which. So I just picked x1 to be above the town and x2 below the town. We are talking about mean. So my parameter is the mean oxygen content above the town, and the other one would be the mean oxygen content below the town. Since I did call x1 the oxygen content above the town, mu1 has to be the mean oxygen content above the town. Can't mix those up. And therefore mu2 is the mean oxygen content below the town. Now we can go ahead and state and check our assumptions. So there are certain assumptions to a 2 sample independent. The first assumption has to do with the type of samples. So there was a random sample of 5 oxygen contents above the town was taken. So you do need to have random samples, and we had a random sample of 5 oxygen contents below the town was taken. So those are the stating parts. We haven't checked it, but we've stated what was supposed to happen. And we can actually say that this actually checks because we were told that both samples were random samples. So we're good. The second assumption of every independent anything, is that the 2 samples are independent. So I've already argued that they were, so we would just now say the stating would be that they're independent. The checking would be that since Some ratings were above the town and others were below, and one value doesn't affect the other values. The samples are independent. And then the last assumption in a two-sample independent is that both populations of the random variables are normally distributed. So the population of all oxygen content above the town is normally distributed, and the population of all oxygen content below the town is normally distributed. Normally you would go through the assessments of normality, such as the normal probability plot or normal quantile plot, the histogram, and the number of outliers, and you would do that for each sample. But we were actually told in this problem that the populations are normally distributed. So we don't need to worry about it in this case, but in most cases that's what you would do. So now we can get to our next step. Our next step is to find all of our sample statistics and then the confidence interval itself. So I would use technology of some kind to find your sample statistics. You do need to know what your sample means are. So we'll call the sample mean for the first sample x bar 1. Turns out that's 5. S1, we are told, or we could find from our technology, is 1.58. You also need to know sample size for the first one, and there were 5 values in that sample. And then x bar 2 is 4.86. S2 is 0.114, and N2 also is 5. In an independent t-test or t-sample interval, they don't have to be the same, but it's better if they are, but they don't have to be. So there's our sample statistics. Now in order to do the interval, we need to be able to calculate E. E in this case is your critical value from your table, or calculated by hand, times S1 squared over N1 plus S2 squared over N2. Now to get T sub C, we need to know the degrees of freedom, and this is where an independent test is a little bit more work. The degrees of freedom are kind of a little bit more work to go through. I would highly suggest that you just use technology to calculate this, but we'll go ahead and do this problem outright just to show you how it works once. So this is the formula for the degrees of freedom. A turns out to be S1 squared over N1, and B is S2 squared over N2. So we already know S1 squared, it's 0.158 squared, over N1 is 5, and S2 squared is 0.114 squared, also over 5. So A turns out to be approximately 0.0049928, and B turns out to be 0.0025992, and that gives us 0.0049928 plus 0.0025992 squared over top of 0.0049928 squared over 4 plus 0.0025992 squared all over again 4. And so the degrees of freedom turns out to be 7.2769. Now, if you're using technology to come up with your TC, then you can actually just use that degrees of freedom to calculate it. As a reminder, what is happening here is on a T distribution, T sub C is here, negative T sub C is down here, and this area is that confidence level that we're dealing with. In this case, that area would be 0.90, or probability. Area and probability are interchangeable here. And then you can use technology to find out what your T sub C and negative T sub C are. And then you can use exactly those degrees of freedom. If you're, however, using a table, then you do need to round the degrees of freedom, and you always round the degrees of freedom down. So your degrees of freedom in this case would be 7. We're going to go ahead and use a table. So we now know our degrees of freedom is 7. We're going to go to our table. We have a table here that has, across the top are your confidence levels. We are 90%. Down this column are your degrees of freedom, and there's my degrees of freedom of 7. and then your T sub C is just where those two row and column intersect. So our T sub C is 1.895 in this case. All right, now that we have all that, we can stick this into the formula. So we have 1.895 as our T sub C. S1 would be 1.58, and then you're going to square it, divided by 5. S2 would be 0.114, you're going to square that, divided by 5. And then you end up with, when you calculate that, that ends up to be 0.17. All right, so we're almost there for our confidence level, confidence interval I should say, I'm sorry. The confidence interval here is going to be, you're going to take the difference in your sample means, x bar 1 minus x bar 2, and then you're going to add and subtract that e. So we're going to subtract that e, and that's going to be less than mu1 minus mu2. And then you're going to take x bar 1 minus x bar 2 again, the difference in your sample means, and you're going to add that e. So we know that our sample means are 5.00 and 4.86. Then you're going to subtract off 0.17, the e we just calculated. And then we do the exact same thing, 5.00 minus 4.86, and you're going to add that e. So when I do this subtraction and then subtract off that e value, I get negative 0.03. And when I subtract these means and then add the e, I get 0.31. So now we can get to, we're done, that's our interval. So now we can get to our statistical interpretation. This was a 90% interval, so there is a 90% chance that the interval, negative 0.03, less than mu1, less than mu2, less than 0.31, contains the true difference in the means. Again, interpretation of confidence intervals is this way. We're not saying that the true difference is in between these numbers. We're saying that we have a 90% chance that this interval we calculated actually would contain the true difference. That is a true statement in itself. There's a chance that you got the wrong interval. So we want to talk about the chances of the interval containing the true difference and not the other way around. The true difference doesn't move, the interval can, depending on which samples you take. So now we get to the real world. Because the lower limit is negative, a negative value means that mu1 must have been smaller than mu2. Because the upper one is positive, that would mean that mu1 is greater than mu2. We don't know what value this difference takes on, so it could take on any of the values in this interval. So it could be that mu1 is less than mu2 by a certain amount, and it could be that mu1 is greater than mu2 by a certain amount. So in this case, mu1 was the mean oxygen content above the town. So we can say the mean oxygen content above the town is anywhere from 0.03 less to 0.31 more than the mean oxygen content below the town. So I do want to make a comment. If both of these are positive, then in that case, the mean above would have been always more than the mean below. If both of these are negative, then that would mean the mean above would always be less than. It's only because one is negative and one is positive that they kind of switch here of less than and more than. The other comment I want to make is that 0 actually does fall in the interval. So since 0 actually falls in the interval, then it could be that the mean content above the town is exactly the same as the mean content below the town. So we can't actually say anything about the inspector's belief that the town is having issues with things. So, but there's your confidence interval.